Hi, everybody. It's Professor Mitchell. We're starting chapter 4 today on the simplex method. And in this video, we'll look at section 4.1 on slack variables and the simplex tableau. In this section, we'll look at standard maximization form, slack variables, solutions using slack variables, group 1 and group 2 variables, the simplex tableau, and the solution corresponding to a simplex tableau. And just so you know, I don't want this to be a big mystery. What we're going to be doing in this chapter is another method for solving linear programming problems, just like we did in chapter 3, except in chapter 4, we will solve those problems using matrices instead of graphs. All right, starting with standard maximization form, a linear programming problem is in standard maximization form if the objective function is to be maximized, each variable is constrained to be greater than or equal to 0, and all the other constraints are of the form linear polynomial is less than or equal to a non-negative constant. So one example that we've looked at together is the chairs and sofas example from chapter 3. That was a standard maximization problem. And in fact, that's, I believe, this problem right here, right? So this problem is in standard form. It is a maximization problem. The variables are constrained to be non-negative, and all of the other constraints have the form linear polynomial is less than or equal to a non-negative constant. A non-negative variable that takes up the slack between the left-hand side of an inequality and the right-hand side is called a slack variable. So before I continue, let me explain what the slack variable represents. So thinking back to this example from chapter 3, this inequality represented carpentry, the available amount of carpentry. This one represented finishing, and this one represented upholstery. So the slack variable for each of those inequalities would represent the unused amount of carpentry, the unused amount of finishing, and the unused amount of upholstery. All right, so we're going to use slack variables to change this problem or this system of inequalities into a system of equations. So you need one slack variable for each of the constraints other than these two. All right, you can ignore these two and then just focus on the other three. So it's traditional to use U, V, and W for the slack variables. So for U, V, and W greater than or equal to 0 and M as large as possible, we're looking for a solution to the system of equations 6x plus 3y plus u equals 96, x plus y plus v equals 18, 2x plus 6y plus w equals 72, and let me put another note in here because this is not quite telling the whole story. So where they got this equation from is starting with m equals 80x plus 70y. All right. We want to write that equation in standard form by having all of the variables on one side. And it turns out for the simplex method, you need to leave the m where it is and move the other variables to be over there with the m. So if you subtract 80x from both sides of this equation and subtract 70y from both sides, you end up with 80x minus 70y plus m is equal to 0. So we have 1, 2, 3, 4 equations. We're looking for the solution to that system of equations that gives you the largest possible value of M. Okay. So this system of equations using the slack variables has an infinite number of solutions because there are way more variables than equations, right? You have X, Y, U, V, W, and M. You have 6 variables and you only have 4 equations. All right, so in this example, we're going to find 2 solutions to this system of equations. And we'll start by writing the augmented matrix for the system. Okay. All right. Now, I need to explain where they're getting this. So if you look over this matrix, notice that several of the columns, and they're going to say this later, I just think it would be better to say it now. Several of the columns in this matrix look like the identity matrix. You see the ones under U, V, W, and M. So the easiest way to get a solution given any particular matrix is to look for the columns that do not look like the identity matrix. So that would be X and Y in this case, and set those variables equal to 0. Okay. Now I might want to use my pen here. Let's see. And okay, so imagine I cover up these columns because we're setting X and Y equal to 0. So that leaves you with this nice identity matrix. It's in diagonal form, like we talked about in chapter 2. And it's very easy to read off the solution. U would equal 96, V equals 18, W equals 72, and M equals 0. So that solution corresponds to the situation where you manufacture no chairs and no sofas. And so you have all the carpentry left, all the finishing left, all the upholstery left, and your profit is 0. So that is probably not the solution that we're interested in. So let's look for another solution. Now to get another solution, bear with me here for just a second. There we go. To get another solution, we're going to have to pivot this matrix to get different columns to look like the identity matrix. So when I was looking this over, I decided I am not going to show my work doing the pivot in this problem. I will do it in the next section. All right. I think it makes more sense to do it because they're saying if we pivot about the element A sub 1, 1, that raises the question with me, well, why would you pivot there as opposed to somewhere else? All right, and we're going to talk about all of that in the next section. But for now, they decided to pivot about the element A sub 1, 1. Remember, that means turning, let me just go back real quick, turning this number into a 1 and turning all these other numbers into zeros. Okay, so that gives us this matrix. So now the columns that look like the identity matrix are X, V, W, and M. So I am going to block out, whoops, to turn on my pen first. Here we go. So if I block out these columns and just read the solution corresponding to the other columns, you have X equals 16. Well, first of all, Y and U are equal to 0. And then X is equal to 16, V is equal to 2, W is equal to 40, and M is equal to 1,280. So in this solution, we're manufacturing 16 chairs, 0 sofas, and we have, let's see, no leftover carpentry, but we have 2 labor hours, was it, of leftover finishing, 40 labor hours of leftover upholstery, and our profit is $1,280. Okay. Now, is that the best solution? Well, we know from chapter 3 that it's not, because it turned out the best solution was to manufacture 14 chairs and 4 sofas. And I don't remember how much profit that gave us. But we're going to talk about how can you tell when you found the best solution. We'll talk about that in the next section. All right, in the preceding solutions, 2 of the variables were chosen to be 0, and the other 4 were solved for using the equations. The variables chosen to be 0 are called group 1 variables. The variables solved once the group 1 variables were chosen are called group 2 variables. Okay, so what are the group 1 and group 2 variables from the previous example? Well, in the first matrix, we chose X and Y to be 0, and we solved for U, V, W, and M. So that makes X and Y group 1 variables, and it makes the others group 2 variables. After we did the pivot, we chose Y and U to be 0, and we solved for X, V, W, and M. So that makes Y and U the group 1 variables, and X, V, W, and M are the group 2 variables. You'll notice, actually, I already pointed it out, that both matrices from which a solution was obtained in the previous example had the columns of the identity matrix present in some order. Such a matrix is called a simplex tableau. All right, so find the columns of the identity matrix in these 2 simplex tableau, and I get a kick out of how they used the French pluralization of tableau here. All right. A lot of times in French, they add an X to make something plural. And by the way, the word tableau just means table, because a matrix is a table of numbers. So it really means a matrix. All right. I don't know who started the tradition of using the word tableau specifically under simplex method, but that's the way it is. All right. Okay, so you can see those columns here. I think if I click, yes, they will be highlighted. Okay. And then in this other one, I don't think we've seen this one before. We're going to do something with it in the next example. There are the columns of the identity matrix. The solution corresponding to a given simplex tableau is obtained by choosing those variables whose columns correspond to the columns of the identity matrix as group 2 variables. The other variables are group 1 variables. So again, the columns that do not look like the identity matrix, you set those variables equal to 0. And those are your group 1 variables. All right, so in this example, we'll find the solution corresponding to this tableau. And I thought it might be easiest to do that if I switch over to the tablet. Okay, so looking over the tableau, I see several columns that look like identity matrix and several that don't. And by the way, you see on here where I've labeled the columns X, Y, U, V, W, M. It's necessary to know which column represents which variable. Okay. So I am going to cover up the columns that do not look like the identity matrix. That would be U and W. All right, it's a little different from on the PowerPoint. I really can't read those anymore, but it doesn't matter because I know that those variables I'm setting equal to 0, and then it's really easy to read the solution. For the other variables, we have x from the first row equals 8, v equals 0, y equals 9, and m equals 7. All right. So yeah, I thought it would be helpful to look at that one on the tablet because this seemed to kind of come out of nowhere, at least to me. All right. So that's actually going to do it for that section. A linear programming problem is in standard maximization form. If the linear objective function is to be maximized, every variable is constrained to be non-negative, and all other constraints are of the form linear polynomial is less than or equal to a non-negative constant. To form the initial simplex tableau corresponding to a linear programming problem in standard form, for each constraint of the form linear polynomial less than or equal to a non-negative constant, introduce a slack variable and write the constraint as an equation. Next, introduce a variable m to represent the quantity to be maximized and form the equation opposite of objective function. Notice objective function is in brackets, so you have to change the sign on every term. Opposite of objective function plus m is equal to 0. Then form the augmented matrix corresponding to the system of linear equations from steps 1 and 2, with the equation from step 2 at the bottom. This matrix is the initial simplex tableau. And that's going to do it for section 4.1. We'll see you next time.